Alright, so everyone, today we're going to be learning about trees and graphs, alright? So, trees and graphs, as we learned before. Um, so, we're going to start learning about trees first. So, the implementation, just like how I'm going to be implementing it, is that we're going to have some sort of object, so a class. We're going to have like a tree. This could be represent maybe like a tree class that then points to a node, alright? And then each node has their own value. And each node is an object, and then they also have left and right subtree pointers that point to other trees. So let's get into that. So first of all, we're going to define a class node, and we're going to have some properties of it. So we're going to have some sort of value, right? That's associated with it. So this in this case is going to be an integer. And then also, we need a node on the left and the right. And this is specifically for a binary tree. If you wanted to do something that had more nodes that like you don't know about, you would probably just, as you can see here, you define some sort of array, right, of children. The reason why it's a node star sign is because it's a pointer. That's the point of it. So that's the pointer, and then also I need to add a constructor as well, just making sure that our data is properly set. So yeah, so that's the node class. So we define some members, so the value, the pointers to the left and the right, and then also a constructor as well, just to initialize the data, for every specific instance of node. I don't know if all of you know about object-oriented programming. If you don't, you might be a little bit lost, but I think you'll be fine. I think you'll be fine. Okay, so obviously we define the node, so each part of the tree has a node. Next, we have to like define maybe a tree. The tree would only represent this root kind of box over here, root object. So most of the time, there's no point in creating a tree class necessarily because you already have access to the first root node. But if you really want to have a tree class, some prerequisites would be that you have a pointer to the root, and then you might also have some other nice functions. For example, I'm just gonna copy and paste this. So maybe you have some other functions like you want to be able to insert things into the tree or destroy the tree. This is just an abstraction, I guess, of a binary tree. But yeah, that's what the tree class would look like. Next, I'm going to get into some traversal of the tree. So some basic traversal. So as you can see, here are the three main ways of traversing a tree. Oh, okay. All right. Never mind. Oh my word. All right, that's unfortunate. But I guess we'll use this. So there's three main ways of traversing a tree. So there's post order, pre-order, and in order, and they're very similar and related. As you'll see later in the code, it's just the difference of me putting a statement elsewhere. So as you can see, in order would be, for example, you would go down to the left. So 1 and then 2. You go down and 3, and then you go back to 4. And you go back up, and you go to 5, and you go to 6, and you go to 7. So you visit the left node first, right? So you keep going, visiting the left node. So then you visit the leftmost node, and you go back up. You visit that node, then you go to the right node, and then you visit the 3. So that's in order. Pre-order would be okay. So the first node that you visit, you visit that, and then you do the recursion for the left and the right. And the left, all right. You visit it, and then you go to the left, and then the right. So as you can see, in order 1, 2, and 3, and 4, and 5, and 6, and 7. Then post order is you keep going to the left, visit 1, and you go back up, you keep going down, visit 2, the 3, and then 4, and then 5, 6, 7. So as I'll show in the code, it's just, I think you'll understand a lot more. So let's do void in order traversal, and we're going to accept a pointer to a node object. That's what that is. So if the node does not equal null, so basically if the node that we've given, since this is recursive, like we need a base case, so if the node is just not null at all, then we're going to do an in order traversal to the node on the left, and then we're going to do an in order traversal to the right. And then, as I said before, this is all about just the order that you like visit nodes, this algorithm. So of course, like we have to obviously recurse to the left and the right subtrees, but in between we need to visit it and do something with the value, for example. So in this case, I would just like to std coot it. Just need to add this using namespace, but I just need to print this out. So that's what that is. So for in order, the basic steps is that you're visiting the left node first, and then once you've visited the entire left subtree, you're gonna visit the actual like parent node. So I guess in this example, when you're at 2, you visit the entire left subtree, so 1, and then you visit it itself, and then you're going to then go to the right subtree. And as you can see at the top as well, 5. So you've done visiting the entire left subtree, and then you're able to proceed to the right. So that's what in order would be. And then pre-order, I'm just going to copy and paste some code. Pre-order is just that you're visiting the parent node first, and then you're visiting the left and the right. That's what that is. That's what pre-order is. So that's why when you start, you visit the very top node, and then you go to the left, and then to the right. And then post order is just going to be this. Post order is just going to be that you're visiting the parent node last. So I think this should be pretty straightforward. Pre-order is that you're visiting a node first. Post is because you're visiting it last. And in order, if you want to be in order and visit the left and then the parent and then the right, like that, then you'd be doing it in the middle. All right, that basically covers trees at a higher level at this point. So I'm just going to then move on to graphs. But just as a summary, a tree is just consisted of nodes. Each node needs some sort of value, and then you just have some pointers as well to some other nodes. This could be like explicit just variables, the left and the right for a binary tree, or you have an array of them. And then we have you can also abstract the node and have a tree class, which points to the root node, as you saw in the diagram. This is the root object and just points to the root node. And then we have all 3 traversals that we're able to use to traverse the tree. They're all recursive. It's just that if we're not on a leaf, then we can recurse to the node's left side and its right side. And then once we've visited, we're going to do something with it, like print it out. And in order, pre-order, and post-order, whatever order you want to like traverse the tree, it depends on where you put this visit statement. All right. So then let's move on to some graphs. I'm just going to delete this. All right. So for graphs, as I said before, we have 2 implementations. We have an adjacency list and a adjacency matrix. Excuse me. So for the adjacency list, as you saw if you were here for last week, it's just a list of all the nodes and then they have some sort of array that shows the connections that they have. So I'm going to show you how to implement an adjacency list. So this would be an example of a graph class. See the graph. We have the number of vertexes just initialized. We have a 2D list. So this is actually going to become a array of lists. As you'll see, I have a constructor as well. It might seem weird with the C++ and like the pointer being there. Like, how is that an array? If you wanted to know, arrays and pointers are basically equivalent in C++. It's a language-specific thing. I wouldn't focus on that though. I also have some other members as well. We have the constructor. We have DFS and BFS, and we're going to add an edge. So just here, when I'm initializing the graph, I have the number of vertices. So V is going to be equal to the number of vertices that we want. So like this is the number of nodes. So like if you have 6 nodes, we're able to do that. And then this is just initializing a new adjacency list for this graph object. So as you can see, it's a list. So this is the type, but this shows that it's an array of lists that are integers. So it's 2D. As you saw here, it's 2D. As you can see. All right, and then moving on from that, we want to add an edge as well. So I just have a function just to manipulate the 2D array of the graph. And adjacency matrices and adjacency lists are both implemented basically as 2D arrays. It's just that their contents are a little bit different. And also, just like with the code I have, it's just an abstraction with objects and classes, because sometimes it's a lot easier on like the human mind with like the object names, as well as you're able to add other specifications. So this was just the graph I have of the add edge. So I'm just saying basically the adjacency list at this index, so basically this vertice, because each vertice is going to be 0, 1, 2, 3, 4, 5, basically in our adjacency list. We're going to be doing that. All right. This is a lot to go through. Apologize, but it's okay, I guess. But yeah, that's just basically how a graph works. It's just the basic implementation. And then an adjacency matrix. This would just be a 2D array, just the number of nodes, 10 by 10. And then, as you saw before in our previous slideshow, it just shows the connections and weights as well and direction, just by saying you have index 0, and then that's connected to index 0 as well. And then depending on the value, if it's like 1, that shows a connection. If it's not, doesn't show a connection. So yeah, that was what we covered last week. But it's as simple as you just creating a 2D array. And then with all this, I guess let's get into some traversals. So DFS and BFS, I promised that I would show these two algorithms this week. Something to note about DFS and BFS is that it's very efficient on an adjacency list, because each time you visit a node, you're able to directly get a list of all of its children. That's why DFS and BFS are very easy and very efficient with an adjacency list, but they're not as efficient as an adjacency matrix, because you have to loop through all the values down a column. It's just not as good. But yeah, so with DFS and BFS, there's just some key things to take from this. All right. So for my DFS I have 2 functions actually, because for graphs unlike trees, you need to mark some of these as visited, because if you're visiting 3 and then you go to 2 and then you go to the 1, it's very possible that you'll end up back at 3 and then you'll just go through an infinite loop. And to prevent that, we mark each of these nodes in an array. So in our graph, we mentioned that we have a connection to each node, right? Then for DFS, we just need to have a initially just call DFS and then just create a new visited array. And then at each index, it's just showing each vertex or node. And then we have a for loop, just setting that everything to false. And then we're going to call our recursive function DFS util. And the only point of this abstraction of having DFS util and DFS is because we need somewhere to store this this visited array. So this is where the main code would be at. We obviously have the visited array that keeps getting updated every time we call DFS util. So we're visiting basically vertex v. So at index, like at this index. So this is equal to true. We're gonna print it out, and then we have a list. And this is just an iterator, just to go through the vertexes of the vertexes that are connected to v. So this is the point of this. This is just C++ code. So the main takeaway of DFS is that we're iterating through all its children, and then as we see, if it's like not visited yet, then we're going to visit it and we're going to recurse. So we're going to call DFS util. So our base case is basically saying that if it's visited, we're just not going to do anything about it. So that's the takeaway of DFS, is that it's a recursive solution where we're going to have some sort of visited array that we can mark each of the nodes, and they're denoted by the index, because an adjacency list just has each vertex at each index. So we're able to determine them that way. And then once we visit it, we mark it, and then we're going to loop through all of its children. And then if it's not visited, then we're going to recurse to it. So that's DFS. And then I'm just going to look through some BFS code as well. So BFS, in contrast to DFS, is actually a iterative solution. So as DFS, as I said, we're going to recurse. BFS, we're not going to recurse at all. Instead, we're going to use a queue. So that's why we don't need a BFS util. So we have a visited array. We're going to just set that all to false, just with the for loop. So I'm just creating a queue right over here. So it's a list of integers, and each integer, of course, as I said, is just a way to indicate each of the nodes. Each of the nodes is denoted by their index in the graph object, the graph class. So we're going to basically first visit our first root node that we're starting from. So this is S is the start. So we're going to set that equal to true. We're going to push back that value to the queue. So and this queue is responsible for our loop that we're going to be while loop that we're going to be running, to basically say that we're going to visit this node, and then we're going to visit this node. So we have an iterator here. Sorry. So we have an iterator here, just I. This is a list iterator. If you guys, I think we covered this in previously, but this is just the way C++ we're able to iterate through these objects. Python already has that in for I in loop, for example, but C++ we have to define the iterator. So we're going to have a while loop, and we're going to continuously run this while loop until the queue is empty. So we're going to run this while the queue is not empty. So first thing we're going to do is we're going to dequeue a vector from the queue and print it out. So we're going to take our queue, and we're going to take our first value, and then we're going to take it out. So we're going to pop it from the front, and then we're going to have a for loop that just runs to basically visit every single child of this like node and check if it's been visited. If it's not been visited, then we can visit it and set it to true, and then push it back to our queue. So that would be BFS. It's that we're using a queue and we have a while loop. That's the thing to remember. We have a while loop in a queue. And then DFS, as I said, is a recursive solution. What we're doing is we are going to visit a node. We're going to loop through all its children. And then if it's not visited, we're going to recursively call itself. So that was DFS and BFS. And if you want to see the code working, sorry for the phone call. I can, for example, add some edges. So first we gotta instantiate a graph object. It's a length of 4, so it's got 4 vertices. And then we're gonna add an edge. So it's a connection from vertices 0 to 1. As you know, an array starts at 0. So we're gonna have vertices 0, 1, 2, 3, and then we're gonna add a bunch of other connections. And then we have DFS and BFS. So we're gonna run this, and then that goes 2, 0, 1, 3. And then we have BFS. All right. So just going through the code, a lot of this makes my eyes very sore because of all the pointers and the language specifics. But the key takeaway, of course, as I said, with DFS and BFS, is that BFS, you should be looking at the theory. So remember that it's a while loop and you're using a queue. And then BFS is recursion. All right. I guess that's it for my part. This is just the basics, but we're gonna get into some actual problems utilizing some of this. If Cristian wanted to open that up.
Yep. So let me just share my screen here.
If I was a little bit unclear, I apologize. But we're a little bit cut for time. I don't really have too much time to go over this. I think it would be more important to actually see the implementations.
Okay. Let's jump into the first problem, I guess. So the first problem we're going to go through is the water jug problem. So the problem is as follows. So you have 2 jugs, one with an m liter capacity and the other one has an n liter capacity. And you want to measure out d liters of water, where d is smaller than n. But the jugs don't have any markings on them. And you're allowed to fill the jugs with water, you're allowed to empty them, and you're allowed to fill another jug with water until one of them is either empty or full. And, given m, n, and d, how do you print a sequence of moves, or print a sequence of moves that will leave d liters of water in one of the jugs? Or you can also print no solution if there is no solution. So here's a sample input and a sample output. So let's say the first jug has a 4 liter capacity, and the second jug has a 3 liter capacity. And we want to get 2 liters in one of the jugs somehow. So one way to do that is to fill the second jug completely, pour all the water from the second into the first, fill the second one completely again, pour the water from the second into the first again, and this will leave exactly 2 liters in the second jug. And then, you just empty the first one so that there's 0 left in there. So that's cool, but how do we do that? So it can actually be solved with BFS, and the problem can be thought of as a graph problem, where the amount of water in the jugs can be represented as a coordinate pair, AB, where A is the amount of water in the first jug, and B is the amount of water in the second jug. And then, each node in the graph would be a coordinate pair indicating the levels of waters in the jug. So we would start at the node with coordinate pair 0, 0, aka 2 empty jugs, and then we can travel to other nodes through some different moves, like filling them or emptying them or pouring. And we want to find a path from the origin to either the D0 or 0D node. So here I kind of have an example of a graph. So we start at 0, 0, and then we can either fill the first node, the first jug, or the second jug. So then we have 2 nodes after that. And then from there we can either fill the opposite jug and get to the same thing, or we can pour some amount P from each one into the other jug. And yeah, where P is, like in this case, if the second jug is completely full, actually I'll show it in the code, but P is the amount, it's like the minimum of either N or the amount left that you can pour into the first jug. I'll explain that more because yeah, it's a little confusing. But yeah, basically you want to traverse this graph, and we want to get to either 0D or D0 somehow. So in this example I use BFS, but you can use DFS as well. And we'll see an implementation here. Okay, so let's run from the top of the code. So the first thing we do is we have our includes. So yeah, we have IOStream, and then I'm using queues and maps as data types in this implementation, and then for convenience I also just specified some string constants at the top, so we don't have to write all this out. So let's hop into main and see how this works. So the first thing, we read our M, N, and D from the input from stdin, and then we see out the output of this BFS function. So this is our breadth first search implementation on this problem. So let's see how that works. So the first thing we have in here, we have our definitions of all our variables and just like initialization. So the first thing is we have a search, something called a search queue, and it's a queue of a pair of coordinates and strings. Oh, I should mention as well, I've defined a pair of integers to be just coord, just for brevity, because I don't want to write this out every single time I have to mention a coordinate. So I just have it type def as a coord. So we have a pair of coordinate and a string. And the reason I have a string paired with the coordinate is because, for convenience sake, in order to get, like this string basically represents some set of moves that will let me reach this coordinate. So that makes it really easy. If at some point we end up finding 0D or D0, we can just output this string and we're done. So it makes it really convenient that way. And then we want to start from some point, so we're starting from the 0, 0 case. Both jugs are empty, and it takes no moves to get there, so empty string. And then with BFS, you have the map of checked coordinates. If I actually show you here in the example, you can see, if we didn't have that array, or sorry, that map, we could potentially have an infinite cycle, right, where we fill the first jug, fill the second, empty the first, empty the second, and then we just go on infinitely. So you need that checked array there. And then these are just some temporary variables that we use inside the main loop. So while this queue is not empty, while we're still looking through nodes, the current point is the front of the queue and the first value. So we want the coordinate. And then the moves to get there is just the second value in this pair, so the string. And we pop it from the queue. So same thing that Kevin just explained. And now we have our main actual code to do this. So the first thing we want to do is we want to check for completion. We want to see if we're at the D0 or 0D node. Actually, what we do is we check if either of the coordinates is D, because if you think about it, even if the other one is something else, we can just empty it, and then we'll be left with D0 or 0D. So we just do some simple if-else. The first one is D and the second one is 0, we can just return. Otherwise, we just empty the other jug and return it. And the same thing, but vice versa. That's cool. And now we get into the casework. So how do we traverse this graph? Well, we have 3 different actions we can take. So the first thing we can do is we can set either of the coordinates to 0. And that's pretty easy. It's just emptying the jug. The second thing we can do is to fill one of the jugs, which is to set either the x coordinate to m or y coordinate to n, the capacity of the jugs. Or the third thing we can do is pour water from one of the jugs to the other until one is full or empty. And I'll explain how we calculate that when we get there. So let's look at the first case, which is where we empty the first jug. And so the new point is just 0 and whatever our second jug capacity was. That's our new node. And so if we haven't checked this node yet, then we push it into the queue for checking later on. And the node is just the coordinate, and the moves plus, we had to empty the first coordinate to get there. So you can see how that accumulates as we make moves. And then, yeah, case1.b, the exact same thing, but we empty the second jug instead. And so we add that to the moves, same code. And then case2.a is where we fill the jugs. So in the first case, we are filling the first jug up to m, and we leave the second one the same. So if we haven't checked this point yet, then we want to push it to the search queue for checking later on. And again, we add the fill first to the moves because that's what we're doing. We're filling the first jug. And remember, these were the string constants I defined earlier, just that I don't have to type out fill the first jug, new line every single time. And then case2.b is the exact same. It's just the new point is the same. It's the same first capacity, whatever it was, in the first jug, and then n, because now we filled the second one. And then, okay, now let's look at case 3, which is where we pour water from one jug to the other. So the amount we pour, if you think about it, and this is the case where we pour from the first to the second, is whatever we have in the first one. It's the minimum of either whatever we have in the first one or the amount left, like the empty space in the second jug, right? Whatever comes first, that's the lowest amount. So you can't pour more water than there is in the first container, and you can't add more water than the empty space in the second container. So that's why we take the minimum of these two values, and that's the amount we're pouring, so we subtract that from the first jug, and we add it to the second one. And again, if we haven't checked this value yet, we add it to the queue, and we add the moves as well because we're pouring from the first. And then case 3.b is the exact same, but vice versa. This time it's from the second, and this is the space remaining in the first. And so we add the pour value to the first one, subtract it from the second, and do that. And then we also have to make sure that we checked the current point. And then we just keep going through this queue until it's completely empty, until we've checked all the points. And then if we haven't returned yet, that means there's no solution, right? If we check all the points and there's no completion case in the entire, through all the points, that means there is no way to reach the desired case. But otherwise, we would return inside the queue. So, yep.
Can I just quickly jump in here and mention that attendance is open, so you should go and log that. If it doesn't work for you and you didn't just recently join, let me know in general and I'll log you manually.
Yep. So actually, this is a perfect time to ask some questions. Does anyone have any questions about what I've covered so far? I'll actually check the chat here.
Okay, I'm just gonna mention something though, guys. But I guess this was a good example of BFS, but also it was an example that showed like BFS. If you need more data as well, that's how you get into language-specific stuff. You'll add some abstractions. Sometimes just like simple numbers will also be like more complex objects.
Mm-hmm. Also, Eric, I'll provide the slideshow with all the links at the end of the presentation. I think Tatus is typing something. I'll just wait for him to finish. Also, Kevin, you're still live. So I guess that's a good question. If you think about it, BFS, you're looking basically closer to your starting node, whereas DFS, you're going depth first. So you have to think about, in which situation, like it's problem specific basically, and in which problems do you want to go deep first, or in which problems do you want to just kind of search the nearby values first. So that's basically how you determine if you're using BFS or DFS in a graph problem. Now I'll just I don't remember CCCS2 last year. What was that one?
It was again. CCC S2 was the question that had to do with a graph. Everyone was talking
Oh,
about
yeah,
it.
yeah, I remember now.
It's like factors. There's a bunch of like yeah, multiplication numbers or something.
It was some sort of maze.
Yeah.
It
Maze,
was a
yeah.
maze that you had to navigate.
Yeah.
I don't remember that problem too well. I remember everyone talking about it though. Yeah, I would have to look into it, but I can talk to you after about more efficient solutions. Okay, awesome. And
I will mention that I'm going to guess that it's probably more efficient, like in a situation in a like a maze solving solution. It's probably better to use DFS, and the reason why is that DFS, all you need to do is find the direct path all the way along. So you'll basically be checking like each pathway, I guess. But BFS, you're probably going to cover like all of the possibilities. Like you're going to cover more ground.
mhm.
If that answers that question, like better. But
Awesome.
yeah,
Yeah,
let's go to the question.
Harry, yeah, I'll be posting the link to the slideshow, so you guys will get all the links. I'll be posting it in like the announcements probably or something like that. Yeah. Okay. I guess we can run it. I can show you that the code works. 4.3.2, I believe, was the data we had in the slideshow, and you can see that outputs um, the correct solution. You can verify on paper that works. So, yep, that's cool. I guess we'll move on to the second problem then. So, up here. Now, the second problem is pathfinding with Dijkstra's algorithm. So, you're given a map with some uncrossable terrain, and you're given 2 points on the map, 2 coordinates, and you want to find the shortest path between these 2 coordinates. So, I'll show you an example of what I mean. So, here's like a map, and you can see this like dark gray squares are terrain, and our blue value is our starting point, and our red value is our endpoint, and we want to find the shortest path, some way through here, that avoids this terrain, and we want to do it algorithmically, obviously. Like, you can look at this, you can see obviously there's a path this way, there's a path this way, there's a path this way, but what if I give you a 1000 by 1000 map? You have to be able to do this programmatically. So how do we do it? Dijkstra's algorithm is one way. There's also like A star is another algorithm, and there's a lot of pathfinding algorithms, but Dijkstra's is the simplest. So let's see an implementation in CPP. So added some more comments in this one, so it should be easier to read. So the first thing we do is we include all of the libraries we'll need, or packages. So here we have IOStream, vector, limits, queue, and algorithm. And we'll see as we use them throughout the code. Again, I define a coordinate as a pair of integers just to avoid typing that out. And this is the same code we saw from a couple lessons ago, just printing a coordinate pair. Again, these are all like, these 2 things are just convenience. Okay, so let's look into our main function and see what this does. So we have a bunch of integers defined up here, and here I kind of have a little matrix showing what they do. So m is the height of the map, n is the width of the map, sx is the starting x coordinate of the map. So sx and xy would be like this point right here. And then I have dx and dy, which are the destination x coordinate and destination y coordinate. And then t is just some temp var that we use later on. So yeah, dx and dy would be down here at the bottom of, in this case, they could be anywhere on here that's not terrain, but in this example, I have them set to 99, so the bottom of the map. And yeah, we read these in from SCDN from the terminal, and we read, yep, m and n as well. And then we want to populate our terrain array with inputted values. So I can kind of show you actually what an example input would look like. So you can see here, these are starting x and starting y. This is the destination x and the destination y. And then this is the width of our map. It's just a 10 by 10 map. And then here I have a bunch of zeros and ones. So in this code, a 0 means there's no terrain, and a 1 means there is terrain. So when you paste this in here, this loop here will go through each value, and if it is terrain, it'll push back a boolean that's true into this 2D vector here, and that's how we parse it in the code. So I can kind of show you how these loops work. So we define here a vector of vectors with boolean data type, and we loop over the height and the width of the map. So every time we loop over the height, we want to add a brand new vector. So that's basically just adding each row as we go down. And then, for each element in the row, we would read it from the terminal, and then we would push back if it's equal to 1. So remember how I said 1 is terrain and 0 is not terrain? So here, yeah, you can see how if t is 1, this is true, and if t is 0, then this is false. So that's how we kind of set the terrain in this 2D array. And then we call this Dijkstra function on the starting coordinate, on the destination coordinate, and with a pointer to this 2D vector. So let's see how this function works. So it's kind of a jumble of code here, so let's go through this. So this function Dijkstra returns a pair of an integer and a pointer to a vector of coordinates. So this integer will represent the minimum distance, and this vector will represent the path of. It's just a vector of coordinates. So yeah, an array of coordinates. Yeah, that'll be the path, the shortest path. And so yeah, it takes the starting coordinate, the destination coordinate, and the terrain, and yeah, it'll return these values. So let's see how it does that. You should already be familiar with Dijkstra's algorithm. I believe it was covered in last week's lesson. So I won't be going too into depth, but I'll show you guys kind of how it works. And again, you can consult this Wikipedia link for a pseudocode algorithm that it's pretty similar to what I did. So the first thing we define here is a vector of ints, and this is the distance array with the shortest distance from the start to whatever point you index it at. And then we have this array called prev, and it's the previous point on the shortest path from the start to the given point. So if you index it at some coordinate, let's say 1, 2, it'll give you the shortest, the point before it on the path to the start, the shortest path to the start. So yeah, if you think about it, you can trace this backwards, hopping point to point to get the shortest path from the start to whatever point you want. And then, yeah, we also have a queue of points on the map that we want to look through. I'll explain about this one later as well. So first thing we do, we want to initialize all these vectors and whatnot. So we iterate over the rows, the number of rows. And each time we push back, an empty vector. You can use these curly braces to do that. CBP is smart enough to know that when you do this, you mean just like a new empty vector. And then you iterate over the size of the rows, and we push back infinity. So if you're familiar with the algorithm, by default, all the values in the distance array are set to infinity. You can't quite do that because by default, integers don't have an infinity value. They must be finite in CPP. So we just set it to whatever the maximum integer is. This is why we use that limit package, and this will work pretty much always, unless you have like a giant map that it will have to be like I think 2 to the 31 before this breaks. So yeah, we just set it to the maximum integer, which is like quote unquote infinity in our case. And then in the previous point, we just set them all to -1, which is like our way of saying undefined. And then again, if you remember the Dijkstra's algorithm, you have to set the first starting point has to be set to 0, the distance. And then we also want to push the starting point into our queue of points. And then here I've defined some variables for our loop. I guess the only thing to notice is the max y is just the number of rows, and max x is it's like the width. Also, something I should point out is because of the way I did it, the terrain is in row major order. So row major order basically means that I guess how you think about it's like the first. So let me find an example here. Like you see how every time I'm doing like this I do like one square bracket and then the other. There's two indexes because it's a 2D array. The first index refers to the row, and the second index refers to the column. And if you think about that, that means that the first index is actually the y coordinate, and the second one is the x. So it's not x, y, it's y, x, it's reversed. This makes it easier when you're writing code instead of column major order, but yeah, that's just a caveat to remember that you have to flip the coordinates when you do row major order. So anyway, let's run through our loop. So while the queue of points to consider is not empty, we want to take whatever point is in there, and we pop it from there, and then we get the distance to this point that we found so far, and we increment it by 1 because we use it to consider the distances from here on. So the distance from this point to any other point nearby is just 1 more than whatever distance it took to get there. And now we check each cardinal direction. So let's look at the code for the x plus, or in this case, it's actually y plus 1 case. So the first thing we want to do right off the bat is to make sure that the point we're looking at, this new point, is within the bounds of our map. Otherwise, you'll segfault, so segmentation fault, which happens if you try to access or do stuff outside of the array range. So in this case, yeah, we checked if the first value is within the number of rows, and if the second coordinate is within the number of columns. And we also want to check if there's no terrain at that spot, because if there is terrain, then we don't want to consider this case. And then, yep, just like regular Dijkstra's, if the distance that's currently set is greater than the distance that we found in this iteration through, then we just want to update it with this new distance, and we want to set the previous point to the current point. And then we want to also push this new point because it has to get updated with the new distance. And so again, it's the exact same code for every other case. These are the cardinal directions, like this is y plus 1, y minus 1, so x plus 1, x minus 1, that's down, up, right, and then left. And yeah, there are more efficient ways to write this code. If you notice, I'm literally pasting this exact same code block every single time I update the new point. You can make this a function instead. But yeah, if you're maybe writing a coding competition or a hackathon, it's fastest to just paste it, even though it's not technically the most maintainable or best solution. And then yeah, we keep going through this loop. We keep updating and traversing our map and updating it with the shortest possible distance we can find. And so that's cool. So now we have the dist and the prev array populated. But now we have to find the shortest path. So how do we do that? Well, remember, we can actually trace the path from the end. So yeah, so first thing we'll do is we'll define a new vector of coordinates. The reason I use the new keyword here is because I want to return this. Remember, if you don't use it, it's just a local variable and it'll get deleted when you exit the scope. So you have to use new. And that'll also give you a pointer, so that means you have to do pointer stuff from now on. And yeah, and then we set the current point to the destination because that's where we want to trace from. And then basically, while we're not past the origin, we want to append the current point to the path. Then we want to get the next point by looking at the prev array and seeing what point it tells us to go at next. That's what I kind of mean by jumping back through the map. We use this previous array to tell us where the previous point is in the path. And then you might ask, okay, why is the while loop saying not equals -1? And this is because, remember, so at the very start, we defined everything as -1 and -1. And now when we run this algorithm, all of the previous array elements will get updated except the origin one. Because, nothing can ever be, you can't have a shorter distance to the origin than what we have by default, right? So it'll always be -1, and that's just how we check. You could also just do while the current point is not at the origin. That will also work. And then, yep, so then once we're done tracing that entire path, we have to remember that the path is in the reverse order because we started at the end. And so we have to use std reverse from std algorithm to reverse the path. So you just pass it the begin iterator. the end iterator, and it will do that for you. And then we return that, the path as well as the distance to that destination point. And then, yep, so now we're here. And now we just do some printing. We want to print the minimum distance and the shortest path. And so then we just iterate over the coordinates that we receive. And we just print the coordinate pair. But we have to remember, again, we have to reverse, just like I did it here. You have to switch the x and y values because we did row major order. And then you have to remember to delete the allocated vector, or else you get a memory leak if you do more stuff with the program, because we called new. And then, yep, so I'll just show you the code. So this is the same graph that we had in the slideshow. I guess I'll show you quickly to refresh your memory. So it looks like this. And I've basically just converted all the dark squares into ones and specified the same ending and starting coordinates and the size. Yep. So yep, copy all that. And then we'll run the program. And we'll just paste that into there. And so it'll tell us the minimum distance is 20. And the shortest path, it'll just dump all the coordinates here. And so I've already parsed those for us. So if I'll just top here, actually, it'll look like this. So this green path is the coordinates that it spits out. And you can verify manually, if you look at the other cases, this is the shortest path. And it has a distance 20. So yep, that's a programmatic approach to finding the shortest distance using Dijkstra's algorithm. So actually, if you guys have any questions, I'll take those now. Yeah, var_t was the temporary thing I just used to see if it was a 1 or a 0. Yeah, not terrain. It's just a temporary thing.
I just wanted to mention as well, guys. If you didn't know, like we had that while loop, and it does not if it's not empty, similar to BFS, right?
Okay. Yep, the code will be posted as well if you want to look at it manually, and you can always PM me questions about it. Yeah, I'm online most of the time to respond. Okay. I think that's pretty much it. Yep. Thanks for watching, and so all the links will be posted in the announcements channel shortly, as well as VODs. And yeah, feel free to PM me questions, because I know running through this code in such a short time, it might not be the clearest explanation, but I can do my best to clarify it with you after if you have any specific questions. So yeah, thank you all for meeting. I guess meeting adjourned.